So let's turn to the semi-classical limit. So now this is more conceptual. So the first thing was really just the motivation for you to sit down and try to do it, because this way one kind of, like, maybe if one is first, like the tendency if you have objects which first seem new, you have to, of course, get used to it, to use maybe the respect of them, and one way to do it, I think, is just go through the single part problem, because it see somehow how it's doing. So now we are going to this conceptual problem of the semi-classical limit. So let's start off with the quantum mechanical propagator in the Lagrangian version, where we have a set. So to calculate the transition amplitude, what is the amplitude to propagate from initial point to some final point at some time t? Well, integrate over all possible paths in the Lagrangian version in coordinate space, which connect those 2 points at time t, and then weigh each path with the classical action associated with this trajectory. So let me just recall that in this integral, all paths u of t from, so connecting these points to initial to final at time t contribute to the sum. So if we take some 2 points, well, we have a given path that will contribute to the sum, but we will have, like, might be that this is some path that comes close to a classical path, if there's some potential, and this path somehow takes an optimized version. But then there will be also very strange paths, like, which do not look really like paths that you would expect thinking about the problem classically, but what the propagator tells us that all of these paths actually contribute. Now, in some way, what we're interested here is we see that each path is weighted by the classical action divided by h bar. So quantum mechanics here is always visible, but then also we see that, like, the classical limit should appear, because in the classical limit, well, the action doesn't, it's a classical action, so it doesn't depend on h bar. So if you have a purely classical problem, we have here some action which is scaling as h bar to the power 0, so it's independent of h bar, and this is scaling as h bar. So, like, you can think about, well, if you would have, for example, a free particle, this is just given by the integral over the momentum along the coordinate. Also, this is in a way, if you have compare the wavelength of the particle to the length of the path. So if you have a classical object, the mass is large or whatever, if the wavelength is typically very much smaller than the typical distance you're interested in, this is a very huge number, no? So you can always, like, think in a way of the classical limit ascending h bar to 0, meaning that here you have like for classical problem, action scales that are independent of h bar. So this can become a very large number, and the question is, well, we should somehow see that the classical word emerges. So if we strictly set h bar to 0, classical physics should appear. So how do we see in this path integral that in the limit where this action is much larger than h bar, or let's say this is the limit of sending h bar to 0, we can see that somehow the classical paths are those which really only contribute in this integral. Okay? So this is the question that we want to ask, and as I said, we will always talk about, like, semi-classical limit as a limit of h bar going to 0, but this just means that the typical action scale associated with the typical path we're interested in is much larger than h bar. So typically so it's a classical action scale. So this is the question we want to ask: how does classical mechanics emerge in the limit h bar to 0? And then what is, like, remaining maybe from quantum fluctuations of h bar small so finite but small. Now, this is all within the semi-classic limit, and this is actually a very conceptually very important point, because there's really branches of physics where what we are going to discuss is a discussion then of many problems. So just maybe one motivation, like what one typically, well, one thing that people started to wonder is, well, what is the quantum mechanics of a Hamiltonian which is classically chaotic? So I take some, let's say, chaotic cavity, like we have boundary sketching that gives rise to classic chaotic motion. Are the signatures of this chaoticity once I turn to the quantum problem? So instead of talking about quantum mechanics, I talk about the quantum problem. And it turns out that, well, one very nice way to think about it is if you have a formulation where you can still think about the things that you use to describe chaos. And also you want to somehow have a formulation, for example, in phase space, and talk about still trajectories and what does it mean, like chaos in classic system, that you have like divergent trajectories, exponential divergent time given by some of the outcome of experiments. And you can now, using this formulation, nicely see like aspects of chaos in quantum mechanical systems. So what does quantum mechanics mean? Well, you have still wave properties, so you can have interference with all these things. So you can see all this nicely here using this formalism, or starting from the formalism that we are going to write. So there's many problems where this gives you the first intuition. Okay, maybe I'll discuss one brief example at the end from like condensed matter, where you have, like if you take a small piece of metal and you calculate, you measure the resistivity or conductivity of the small piece of metal, you see that when you go to very low temperatures, you have some weird magnetic field dependence, which like classically you wouldn't expect. And well, there's one thing that already we recognize. Well, you have to go to very low temperatures to see this effect, or you can suspect that this has to do something with interference. So once you go to high temperatures, you can have incoherence, so it can be some interference effect. And in fact, you can think about it. So as said in the very beginning, well, you have, like, you're interested in the conductivity, you have some small, like, microns or whatever piece of metal, and the typical action scale for an electron to propagate through this distance is much larger than h bar. So in some way, you're in this regime where you can think, well, still as an electron going along some classical object, some classical path, but then there should be something which gives you deviations from purely classical mechanics, because you want to describe this magnetic field dependence. It turns out that it is due to some interference effect, which you can nicely understand of interference of classical paths. So maybe I come back. So how does, this is the question we want to ask, how does, first of all, classical mechanics merge into limit h1 to 0? What are maybe some reminiscence of quantum mechanics? And technically, one can ask, well, how do paths which extremize the action distinguish from generic paths? Well, it would be a classical path, generic path, well, which do not extremize the action, where this function derivative is just not zero. Well, this is the technical version of this question. No? So, if we look at here our quantum mechanical propagator, well, we say we have to sum of all paths, and what we do is we weight every path with some weight. So first, very superficial look. Is, well, we see every path that we can sum contributes to the integral, and the weight of the path is given by the exponential of this here. So if we take the absolute, well, so just look at this expression here. We look at every arbitrary path, so one which maybe comes close to classical, and then a very different one, and we just see, well, all the paths actually come with the same, with a weight which have all the same absolute value name you want. So this is just a trivial observation because we have e exponential real number. So, but what this tells us is, well, if the amplitude is all the same, somehow the phase should tell us the difference between classical and like between those paths and those paths. So it should be some, if it's a phase, then we will say, well, if it's a phase, probably it has to do something with interference, no? So the difference between classical and generic paths should be, lies in the phase, so should be due to interference. And then to explain this better, let's just take like one simple problem that we already discussed once, and that always appears in this form. So we have an integral over just here, like numbers on the unit circle, no? So we have a large integral of all the paths. Every path contributes with a number which is on the unit circle. So all has a weight 1. So if we are in the semi-classical limit, this means that this number here, so the number on the unit circle is the exponential I of a real number which is much larger than 1. So that's the problem we are looking at. Okay? So in a way, let's look at the simplified problem where you have the following. So let's now the second look at the problem. Let's look at what we do. Then we need to have a sum over phases, no? So let's consider large number of reals, phi to phi n, which are all real numbers, and let's assume that all these numbers are much larger than 1. The typical numbers are much larger than 1. There might be some which are of the order of 1 or small, but the typical are much larger than 1. So this is just, in a way, a cartoon of the problem we are looking at. We have a sum of a path, which is here now the sum path integral is sum over phase vectors I plus 1 to n. Okay, so we have, this is here actually infinite sum. What we sum is exponential of the semi-classical limit large numbers. So this is a cartoon, like the sum over exponentials of large e, I times large real numbers, and this one over n is just a normalization. Okay, so this is one just to normalize this. Okay, and so as I said, so these define some complex numbers, I, which are all living on the unit circle in complex space. with this type 2 problem, we can now distinguish actually two cases. In this argument that comes now, we already used also when we took in the construction of the path integral this final step of sending n to infinity. We said that somehow, especially for smooth path in phase space, it contribute integral. So let's consider two cases in this sum. So let's consider first a case where the numbers phi and phi j are not only large, but they're also largely distant. Yeah? So if I take one number, the other one is just completely unrelated to the first number. So they are all in pairs, like not all, but the typical, like most of them are just randomly distributed. Okay? They're all with large numbers. So this would mean that all of the i's, if you think about them, are just randomly distributed so this is like a circle S1, no? Are just randomly distributed over S1. Okay. Well, trivially, all these are large. They are not somehow correlated in the sense that if I take one, the other one is in the vicinity, but just the difference is much larger than the same two pi. So this would mean that if I take here the sum, I have a first, which is number which is somewhere sitting here, like this is V1. Now the next number is, well, it's just somewhere randomly C2, then the next might be here, V3, the next might then jump around. So all these numbers just widely jump around, meaning that if we add a very large number, n of them, it just amounts to summing up random numbers on the unit circle. So this means that the sum of these random phases will be just given by the order of 1 over square root n. No? So the sum, typically, if I take them just random, I mean they are maybe Gaussian distributed with a typical width given by square root n. So this will give me a contribution of square root large n, and I have the normalization factor. So this will give me a contribution of the order of 1 over square root n, which goes to 0 in the limit n to infinity. And what we can say is, well, we have, in a way, destructive interference of a lot of large phases. No? Let's call this just saying it's not really. Yeah, if you have an incoherent sum of large phases, which gives you a suppression. So maybe better word would be incoherent sum. Okay? So that's case A. Now we could think, however, also of another possibility, and this would be that, well, the phases can be very large, as in case A, or as we assumed from the beginning, but it might be that they are not so far distant one of each other. Okay? So this would mean that, well, the phases themselves can be large, but the typical distance between different phases can be much smaller than 1, meaning that then those phase vectors they would accumulate. So you have a number of complex numbers and the numbers accumulate in a direction, some direction on the circle. So it's simple. So you have, let's say, V1 is this, now V2 is in the vicinity, so you have all of those being close to each other. Okay, so this would be just the second possibility. Now if you have this second possibility and you look at the sum here, then you see, well, you can write every of these phases as just some average phase plus some variation. Well, then you have just e to the I phi over n. And the statement here is now that this variation delta phi I is much smaller than 1. So this will give me a contribution of order n. I add n numbers close to unity. So this will then just be some finite contribution e to the I phi. Okay? So this is finite in the limit n to infinity. And what you have is like you have a coherent sum of many complex numbers. So in the way I call this destructive, you could call this constructive interference, but maybe the better way, better statements would be coherent and incoherent sums of things. I think this is not the word. Incoherent sum. These are coherent sum. Okay, so this is just very simple statement, no? Okay, or questions or, but so what does this then have to do with our problem? Well, if you just consider two nearby paths. So we integrate in this path integral over all possible paths. So let's look at the contribution of two nearby paths, okay? Which we call Q of t and Q prime of t, which I write as Q of t, the same path with some deviation, eta, where eta is small in some sense, okay? So consider two nearby paths, and what we can now consider is, or look at is Taylor expansion of the action of the nearby path. We can expand it around one given path. So let's look at the classical action of the path Q prime, which is nearby Q. So we can write, if eta is small, this approximately as the action of the one reference path we were looking at. And then we have deviations, which are given by the Taylor expansion. Orders. So once we have done this Taylor expansion for the classical action of the nearby path, we can look at the contribution of the two paths that we have to the path integral. Well, this is just given by e to the I, the classical action of the path Q, plus e to the I, the classical action of the path Q prime. And now using that this is close by to this, we insert here the Taylor expansion. If we do so, you can write this as e to the I, classical action of the path Q. Then the one reproduces this factor, and here is some d to the I delta phi something different. Okay? This is now difference encoded in these terms here in the tail expansion. So we have here like higher terms, and we have to say afterwards something like higher terms. So here I have to find this deviation delta phi, which now we see takes the following form. So delta phi is 1 over h bar dt eta this is plus then the quadratic term in higher terms, okay? This holds for generic paths. But if you look at classical path, if you would have done this expansion around some classical path Q, well, they are exactly characterized by the vanishing of the first term here, because they're the paths which extremize the action of the classical action. So this holds for generic path, the space vector. But if you look at classical paths, then delta phi actually is given by the second order contribution as a leading term. Now, this already tells us that this is going exactly in this direction that we discussed here in the sums of the coherent and contribution, no? But we have to quantify this still. But what we see is that, well, it's exactly the same way. If you take generic path Q and Q prime, you see that their action is completely uncorrelated, no? So small deviation gives you just something completely different in the action. While if you look at variations around classical paths, you see that the path in the neighborhood of a classical path actually has to first order the same action, and deviations are smaller in this parameter adder. Okay? So now comes, okay, simple observation. So we somehow think that, well, this is then the case which we call case A, that we just sum up in a way a large number of independent or not very much or not correlated phase vectors, which give us the nucleon sum of orders 1 over square root n, while in the classical fluctuations around classical paths correspond to the case B, where the action scales are related, are correlated, so we have a coherent sum, and this may then survive. Just use a picture of what I said, and then try to make this quantitative. So what I just said is, well, you have, let's say here, time axis, you will t, you have here your coordinate space, find the initial coordinate, you're interested in the path, and you see, say you have some generic path, and you see that here, if I take a small neighborhood around them, the action will deviate. So you have deviations of order eta, while in the, this is a classical path, I can look at the tube around these, this classical paths which have more or less the same action. Okay, so here I cannot really define like a tube of tubes of paths which have the same action. Here I can. So let's try to quantify this a little bit. And this is the observation that, well, this scale here, this is a classical action independent of h bar. No? So this is some number, or like if I integrate this, will give me some number which is h bar independent. Here I have a factor 1 over h bar. Okay? So I see that these fluctuations here, once they become of the order of h bar, okay, and always think like h bar 0 always means comparing like action scales. So once these become of the h bar, this already becomes of order 1, and they will become incoherent. Okay? So I can here have fluctuations which the typical eta that can still contribute coherently is an eta which is smaller than h bar. Okay? So small fluctuations. Now if I look at this, the same argument, this is purely classical scale. Okay? So this is h bar to the 0. Now I have here eta squared. Okay? So I see that the typical eta that fluctuates here is of the order of square root h bar. Okay? Now let's just keep in mind the scaling h bar here and h bar, then in the end you can really make this. Or maybe I already made the statement, but we made the statement afterwards. So we say here we have actually a tube in, also defined in the phase space, of the order of h bar, square root h bar, of trajectories which have the same action in the sense that it's delta phi is the number of 1 or smaller. Okay? So this gives a coherent contribution. Now, let's just think about the Gaussian integrals. So here this is already then Gaussian. So if you write now the propagator, how would you write? You have a sum of all paths. You write the paths as a classical contribution plus fluctuations around it. Okay? So here, in this case, we have the contribution from the fluctuations is quadratic. So we have just to, after doing the integral over the fluctuations, this gives some prefactor, some fluctuation determinant. Okay? So here in this case, you can also write the propagator as the term from the classical path plus fluctuations. The fluctuations now have a linear term and a quadratic term. Okay? So here, what we will have is a path integral. If we write, like we have a contribution from the classical action, and then we have a path integral due to fluctuations eta, and they will have 1 over h bar, and then some classical scale here, let's call it, I don't know, c, and then eta squared. And then we have still the linear term here, some c prime, which is also classical. Okay, so this is the term here, but of course you have also here the quadratic part. Okay? In the vicinity of the classical parts, you don't have this linear term here. Is it clear what is written here? Or? Yeah, everyone clear? Or because it's simple, it's not. It's just badly explained. So if I do here now the integral of a fluctuation, it's a Gaussian integral. Okay, so I get this in the denominator, h bar, and then I get, I get this in the denominator, h bar, and then I get this squared. So this is h over h bar squared, and then I have what c prime squared over c. This is all classical, but overall this scale is 1 over h bar. This is classical, so this is really a large number. Okay? So because I have here a linear coupling in the fluctuations, if I would do the integral over the fluctuations, I will see that I get a phase factor here, well, which is just ridiculously large. So I have really a sum. If I look at some contribution, like fluctuation, if I integrate it, it's just a very large random number. So this is like the weird sum. In the case of the classical trajectories, I don't have this term, so I just get some fluctuation. Okay? But this is, I try to understand it. So this is the main observation that, well, around classical path I have fluctuations of the order of a square root h bar, which define the entire tube of path, which all have the same action, which all contribute, while in the generic path I don't have, and this now brings me to the quantum mechanical propagator in the semi-classical approximation.
Okay.
Yes.
It seems to me that these things that you said can be tested. For example, with state experiments. Do you know anyone who has done this to check this kind of thing?
Yes. So that's so I mean there's this this classical. So the classical example. Maybe let me just write down the quantum mechanical propagator in semi-classical approximation, and then I answer your question, okay? Then maybe it comes. So, if we take this observation, we can say, well, in the semi-classical limit, where the typical action scale appearing the weight is much larger than h bar, we can restrict to those paths extremizing the classical action, and if we do so, we arrive at fluctuations around them. We arrive at following expression, which is the propagator in the semi-classical approximation. So you arrive at the following expression. Here I now have taken the case that, I mean, there can be more than one classical path connecting two points in time parameters. So I have the sum of all classical paths. This is a contribution just from the classical path. Okay? This is just the one factor that we pulled out here that we can pull out in all the contributions. So it's just a term that depends on Q initial and Q final and T. And then we have to do the integral over the fluctuations, which, because we are considering classical path, just contains this quadratic term. Okay? So in the generic, there would be a linear term, which then would suppress everything. And this here is now a simple Gaussian integral. Okay? Quadratic Gaussian integral. So if you do this integral, this will give some function f of t. And here I should say that, well, we have here some boundary conditions, which are that the deviations from the reference trajectory at time 0 and t should be just 0, no? Because the classical path that we use already has the right boundary conditions, so the fluctuations here should be 0, meaning that this will just be a function only of the time t and not depending on q initial and q final. Okay? So what we arrive at is can write this thing. So this is the sum of a classical path weighted with a phase factor, which is a classical action, and then we have a contribution which is here from the fluctuation determinant. Okay, this fluctuation determinant actually can be calculated. So this is a function f of tau, and I just give the result here, and maybe we will do the derivation of this as an exercise. I still don't know if this is helpful, but I give the expression here, and you have to believe me that this is what we can show. So we said this is some function f of tau, and what we can show is this fluctuation determinant. We can express purely in terms of second derivative of the classical action with respect to the initial and final coordinate. Okay? So this is the function f of tau that you get from integrating over this tube of close-by trajectories of order of h bar. Okay, so this is the propagator in the semi-classical approximation. And now, just one comment. Okay, let's see how far we get. But if we now recall what we did in the first one, we looked at the propagator for the free particle, and we saw exactly this form. It was e to the I, then it was classical action, and this here you can look back to it. This is just given by exactly this. There should be an I guess, here. I think there should be some I here. Okay, and then we have this fluctuation determinant here. Okay. So, and that was not coincidence, because the semi-classical approximation just relied on what? He said you parameterize a given path at some reference path, which is a classical path. You can always do it and then consider fluctuations around it. In a generic case, you would have to look at then fluctuations either up to arbitrary high order. Now, if you have a Gaussian problem, yeah, then of course the expansion, the functional expansion, stops after the quadratic term, no, in the deviation. Now, if you are clever and do the expansion around the classical path, then you only have the second derivative term, because the linear disappears because it extremises the action. So whenever we have a quadratic problem, we should exactly arrive at this expression. We have discussed one example where the sample was a free particle, and next lecture we will discuss the harmonic oscillator. It's also a quadratic problem. We already know that this should happen, but we will explicitly show this. Now, just let me answer your question. So now we can ask several problems. So you can first ask, well, if you have some interesting geometry, like a ring or a double slit. So what does this tell you? Well, it tells you we are talking still about amplitudes. What you measure in the experiment should somehow not depend on the phase, so it's the absolute square of an amplitude, it's the probability, no? Like you calculate the probability that a particle propagates from here to here, from here to here. So in the semi-classical approximation, like if this ring is much larger than the typical wavelength of the particle, this distance here is typically, this is perfectly fine. This is what we can do. So where enters quantum mechanics? Well, it enters here in the term that we have to sum for the amplitude of all paths. So we would sum here. One contribution would be a classical path going from here to here. Another classical path, I mean, if you don't make some potential barrier or whatever, would be just that the particle goes this way. The same way it can go here and here. So the amplitude, the transition amplitude is given by two paths, no? Path 1 and path 2. So for the probability, we have to take the amplitude squared. So we get this squared plus this squared, and we get the interference squared. And this, then you can, now if you apply some magnetic field here, for example, you see that two parts get a different phase factor to the magnetic field, and then you see the oscillation out of the whole oscillation. Okay, so this is one example where you can immediately see like how quantum mechanics enters, and this is through interference. Okay. Now you also asked about, well, can you say something about deviations from this? No, this is how I understood it. And it turns out that actually people calculated using the path integral. Now, for example, here there are solutions, paths that you can consider where the particle goes this way, okay, instead of going through double slit, but makes it. And they calculate that, well, we have here also paths in the vicinity which have approximately the same action. So they calculated the resulting interference from these paths that you, normally would not take into account. And I think that they're claiming that you should be able to measure it. So if you put in the numbers.
Like, for example, in that result that you wrote, that I think for distant paths, you have this something to the order of the square root of n.
Yes.
I think this is measurable too.
No, this definitely. If you ask like the interference, where comes interference from? So you have to have like the possibility that a particle goes here this way or this way.
Yes.
And this is actually only because, the path is not the classical path, but it's a tube of quantum fluctuations. So in some sense it can here decide because of the quantum fluctuations to go this way or this way. So this is always lies at heart like due to interference. You have some fluctuations which tell you that you can go one way or the other way. Okay? So in this then also, the very similar thing is that the metal that I told in the beginning, so if you take a piece of metal, microns or whatever, at low temperatures, you have some weird magnetic field dependence on it. If you put a magnetic field here perpendicular, and change it only slightly, the resistivity drops. Okay? And this is actually understood in the following way. So if you take here again a metal which is much larger than the wavelength of, let's say, the electron, it should be fine to think in this way about the problem. So if you think about this way in the problem, well, you have this order in the system, and the classical path will be just like diffusively propagating path. Now you would say, well, I have to sum here over all possible paths. Now if I take arbitrary paths like diffusive paths, it might be different, but still the interference term here again is just not, the phases are not correlated, so it should just, the interference term should be suppressed, and the square of the sum should be the sum of the squares, which is just the classical probability. But then if you think about it, then you see, well, there's special paths, very specific paths, which can happen, and this is a self-intersecting path. So if you find that the electron goes here and scatters and then makes some loop and scatters, then you have here the possibility that the electron here goes this way, or it scatters here and goes along this way. Now this possibility to go here along this way or this way is exactly due to the quantum fluctuations, due to this eta squared. This gives you the possibility, to deviate a little bit. Now, if you go this way or this way, if you look at the total action accumulated, that doesn't depend on the orientation if you have a time reversal invariant system. Okay? Then it doesn't matter, so the action accumulated this way or this way is just identical. So here you have found two paths which have the same classical action, so they have correlated actions, but are distinct paths. So this will give rise to an interference term. So what happens if I apply a magnetic field? Well, then I start to distinguish between going this way, and suppress it. If you saw the famous relocalization correction, this one of metals, which they are measured, and this is like the standard methods. Then, so why do you have to have low temperatures? Because you need phase clearance. Now, in the real metal, you have electron-electron interactions, other stuff going wrong, which tells you that you have dephasing. So you can now measure, like, up to what scale do I see this interference contribution by just applying magnetic fields, see if your conductance changes or not. If it doesn't change anymore, you know that your coherence is suppressed. So this is a standard way now to measure the decoherence time, for example, small. So, but this all relies on the semi-classical approximation, on the fact that, okay, classical mechanics emerges because of extremizing actions, but still, the real thing is not a single trajectory, but it's a tube. Okay, this can at some points go different ways. So what still is missing is an estimate of the higher order terms, but maybe make an exercise or make it next week, I don't know, because this was all based on the quadratic term. I motivated by this in combination with the quadratic term is this large phase, but you can, or maybe I give it to you as an exercise. So here, consider classical paths and consider now the higher order terms. What we said is, if I have a linear term, The argument was the linear term is 1 over h bar, linearly coupling to the fluctuations. I get a Gaussian integral which has a weight 1 over h bar. So the weight, if I do the Gaussian integral, goes up, and I get this squared. Okay, so this was how we said that this left 1 over h bar. Now the higher order terms would be here, for example, add off the power of 3. Okay, so now we can just think, well, the typical eta is suppressed again by this term here, by the quadratic, so the typical eta is of the order square root. Okay, then you can just make an estimate of what the higher order terms are and see that they should vanish in the limit h bar to 0 and everything is dominated by this quadratic term. Okay, we'll discuss this in the exercise. And yeah, so this is just semi-classical approximation, and the one thing that I already said, if you have a quadratic problem, this is always accepted. Any questions or this for the Hauptquartier